Hi everybody, we're back to day 2 of our intramolecular bonding notes. So make sure you have watched the first day first, but I'm going to pick up where we left off. So in our last video, we introduced 3 categories of bonding: covalent, ionic, and metallic. And I only started with covalent bonding. I'm going to continue with that today. Yesterday's covalent bonding notes focused on non-polar bonding, and that is where electrons are shared evenly between 2 atoms. Today, I'm going to give you several examples of polar covalent bonding where electrons are shared unevenly. So here's where I'm starting fresh. March 26th, polar covalent bond examples. Note a few things. This is uneven sharing of electrons. And because of that, there's an electron negativity difference between 0.6 and 1.6. So you definitely need to be looking at your periodic table and table S when we do bonding examples. My first example is going to be hydrogen chloride. It's also more commonly known as hydrochloric acid, and it's a molecular formula as shown. The first thing we want to do with this bonding, though, is we want to draw our Lewis structures. So hydrogen has only 1 electron, and therefore it's only got 1 valence electron. Lewis structures show only the valence electrons. Now, on the other hand, chlorine, if you look up on the periodic table, it's a halogen, and chlorine has 7 valence electrons. So when I want to draw its Lewis structure, 1, 2, 3, 4, 5, 6, 7. So the Lewis structure for chlorine shows its 7 valence electrons. I'm now showing an electron dot or Lewis dot structure for this molecule. Now, we do not have even sharing of these electrons because when you go to your table S, you will see that chlorine has an electron negativity value of 3.2 and hydrogen has an electron negativity value of 2.2. Chlorine, being a halogen, happens to be pretty greedy. It really wants that electron. I'm sorry, I'm pointing the wrong one. This chlorine wants this electron from the hydrogen pretty strongly. So because of that, you're going to have a slightly negative end and a slightly positive end in polar bonding, okay? Drawing our structural formula, we could show hydrogen chloride in that manner. Notice 3.2 minus 2.2 gives us a 1.0 difference in electron negativity, and that falls under that rule for identifying a polar covalent bond. By the way, let me show you my ball and stick model. All right, here's our hydrogen, and here would be the chlorine, and the plastic stick represents 2 electrons forming that bond. Okay, so let's go look at another example. Hydrogen bromide or hydrobromic acid. Again, hydrogen has 1 valence electron. Bromine has 7 valence electrons. I'm going to show them as X's this time. Why not? Okay. When we look up the electronegativity values, we're going to find that bromine has a 3.0 value, hydrogen 2.2. So 3.0 minus 2.2 gives you 0.8 electronegativity difference. Okay, so which end is going to be slightly negative? Which end slightly positive? Okay, because bromine is a greedy halogen. And again, we can show the structural formula that way. And here's the ball and stick model of hydrogen bromide. Okay. All right, I'm going to do the third example and final example for today in polar covalent bonding. And this is going to be the infamous water molecule. This one might blow your mind a little bit. So let's kind of think about this here, first of all. So I'm going to start with my hydrogen having its one valence electron. Okay, I'm going to then draw my oxygen. Now, when you look up oxygen, it does have 6 valence electrons. Well, we know for sure one of them's going to go over on this side between that hydrogen. You've got to form the bond. And one's going to go on this side and bond with that other hydrogen. So we've got our H2 and O, but I've got to show all 6 valence electrons in that oxygen. Whoops, making little X's. 1, 2, 3, 4, 5, 6. 6 valence electrons. Now, if you recall from back when we were in school, I actually said water doesn't have a linear shape because oxygen is really, really greedy and it really wants these electrons. It also has 2 pairs of non-bonding electrons, and that is going to impact the true shape of a water molecule. So it is actually better drawn this way. Right? Here's our oxygen. There's 1, 2, 3, 4. 4 non-bonding electrons. And then I'll put, okay, those there. And I will put my little hydrogens down here. So what I've actually made is what we call a bench shape. And why does it have that? Because oxygen is very electronegative. In fact, it's a 3.4. And we know hydrogen is 2.2. Okay, so 3.4 minus 2.2 gives us a 1.2 electronegativity difference. All right, and we're definitely going to have that negative end versus the positive ends here. So when we draw the structural formula, this is really what it looks like. Okay. In a future lesson, we will talk about molecule shapes, such as water, with this bench shape. But suffice it to say, the reason why it's bent like this is there are 2 non-bonding electron pairs on this end of that oxygen, and there's a pull or great desire for electrons, and we end up having a bent shape molecule. Okay, so that's going to conclude my mini lesson for today. You're going to get some practice questions to look at, and please check the class website for those practice questions. Thank you. Bye.